Okay, thanks. I'm Desika. I'm at the University of Arizona. So I'm going to continue our discussion about the IMF, but in a slightly different context. And everything I talk about, mostly everything I talk about, I'll have done in collaboration with Romeo Debe. So I should move this down. I'm allowed. This always happens. So from a galaxy formation theory standpoint, there's a lot of problems, I would say, opportunities maybe, between when comparing the star formation rates from simulated galaxies to those of observed high redshift galaxies that all indicate potential IMF variations. One that was brought to the community's attention by Romeo Debe in 2008 is the so-called main sequence of star formation. So this is the star formation rate stellar mass relation for simulated galaxies, is the pink points, and the observations are the lines for redshift 0, redshift 1, and redshift 2. And as is well known, and this is typical of many different cosmological simulations, there's relatively good agreement at redshift 0. Some slight discrepancy at redshift 1, where the simulated galaxies seem to have star formation rates a factor of a few too low. And by redshift 2, typically the star formation rates of simulated galaxies might be a factor of 5 too low. A good theorist might say that the observations have star formation rates that are a factor of 5 too high, and this might maybe indicate top-heavy IMF at high redshift. And there's a lot of quasi-tentative reasons to believe that this is the direction the IMF could go at high redshift. If you compare the integrated star formation rate density from direct measurements versus that inferred from stellar mass density measurements, and again, this is very tentative. Richard mentioned Naveen's work that makes this problem go away. But if you believe this problem exists, then top-heavy IMF again at high redshift would fix the directly measured star formation rate density measurements and bring them more in concert with the stellar mass density measurements. And there's all sorts of reasons to believe this. The list goes on. Peter Van Dockum showed, if you compare the evolution of luminosity of galaxies from redshift 1 to 0 compared to their color ratios, that perhaps you might find a bottom light IMF at redshift 2 or redshift 3, turning over somewhere around 1 solar mass. And Linda Tacconi showed that if you try to simultaneously model the CO to H2 conversion factor, stellar masses, so therefore getting gas masses, stellar masses, and the IMF, in submillimeter galaxies at redshift 2, you get, and you look at the best fit model in their models, you look at the chi-square minima, which is of the blue line here, which is the best fit model. It typically favors an IMF which is slightly more top-heavy than Chabrier. So the point is that while there's no direct measurements, obviously, of the IMF at high redshift, and you could easily find holes in any of these arguments, they all tend to go in the same direction, that the IMF at high redshift seems to be top-heavy. This is, of course, in seeming direct conflict with what Charlie just showed, which shows that the supposed descendants of high redshift galaxies and low redshift all seem to have a bottom-heavy IMF, such that more massive galaxies have an increasingly bottom-heavy IMF. So this is, I think, a challenge for galaxy formation theory to try to understand. If you believe that the IMF is top-heavy at high redshift, and if you believe the IMF is bottom-heavy and low redshift ellipticals, how do you connect the two? So I'll describe a series of simulations. The first part of the simulation description is pretty standard. It's not using any novel techniques. I run a huge suite of galaxy evolution simulations, idealized disks and mergers. These are just from T.J. Cox's libraries from his thesis onward using Gadget. And when I simulate a large range of masses and merger mass ratios. This is really just to generate a large range of physical conditions. And then, as you'll see, I need the dust temperatures in my simulation. So I'll use sunrise, which I won't talk much about now. I'm sure Chris, Moody, or Charlotte will talk more about this. But it's Patrick Janssen and Joel's publicly available dust radiator transfer code. And if you want, during questions, we could talk more about this. So at this point, I need to make an assumption, because nobody who simulates galaxies simulates down to the IMF, right? So we all have to assume something. So I'm going to assume that the IMF has a shape like a Krupp IMF that has some turnover, and that turnover point varies with the gene's mass in a molecular cloud. And while that seems like it comes out of nowhere, there may be hand-wavy reasons to believe that this could be plausibly correct. For example, if you observe the core mass function, or clump mass function, excuse me, in molecular clouds, this is a Herschel survey, but this has been done for decades, and you look at the clump mass function, it has a turnover point and somewhat similar to the Krupp stellar initial mass function. So you can maybe wave your hands and believe that this is actually a plausible assumption. But nevertheless, this is just a blind assumption that I'm taking for the rest of this talk. Okay, so then we have to worry about the gene's masses and molecular clouds in our simulations. So the gene's mass, of course, goes as t to the 3/2 over n to the 1/2. We simulate down to about 50 parsecs, so we're just simulating the surfaces of molecular clouds. We're not getting very highly super-resolved molecular clouds. So we enforce a minimum surface density in our molecular clouds of about 100 solar masses per square parsec. This is some methods that I developed in collaboration with Mark Krumholtz in the back there. Excuse me. So if we assume a spherical geometry in our clouds, and we have some idea of the surface density, and we figure out what the H2, H1 balance is using Mark's methodology, which I'm kind of surprised no one's talked about yet. I think at this point in the last Joel Fest, there have been like 9 talks about this H1, H2 balance. Anyway, with the H2 masses and surface densities, and assuming a spherical geometry, then I have some idea of what the density is, right? And so I have that term. So the main term, though, of course, is the temperature in my gene's masses, because it's t to the 3/2. So this is, the typical heating processes in the molecular ISM are from the grain photoelectric effect, from cosmic rays, and through energy exchange with dust when the dust is a higher temperature. And the main cooling processes are line cooling. This has been in the literature for quite some time, but revived recently by Mark, Chris McKee, and Adam Leroy. So the main ways to think about this are, well, we know the dust temperature from the sunrise dust radiative transfer calculations, and we'll assume the cosmic rays scale with the star formation rate, anchored by what we think the Milky Way cosmic ray ionization rate is. So the main thing then is to compute the line cooling. So we have to run radiative transfer calculations out of these molecular clouds, so we can make them 1D molecular clouds and consider them isodensity, isothermal, and run radiative transfer calculations to figure out what the line cooling rates are, and then we can solve the system of equations. You do this iteratively because the line cooling rates depend on the temperature, and the temperature depends on the line cooling rates, and eventually you get some sort of temperature for the cloud. And the main takeaway trends to look at are that the cosmic ray heating rate scales with the star formation rate, and that gas-dust energy exchange only becomes efficient at very high densities, above 10 to the 4th. So say I have a very dense system, some starburst Eulerg system. In that system, the stellar radiation field heats the dust, and that dust heats the gas. And if I have a warmer system, a more heavily star-forming system, then I'll get even warmer gas, because I'll have warmer dust and then warmer gas. So you can imagine how this term roughly scales with the star formation rate. And at low densities, where the cosmic rays dominate the ISM temperature, this manifestly scales with the star formation rate. So the combination of those two give us something where, if I look at simulated galaxies and I plot the star formation rate against the gene's mass of the molecular cloud, the average, this is the H2 mass-weighted gene's mass within a galaxy, I see some broad correlation. And if you believe that the gene's mass drives the turnover mass in the IMF, then what you take away from this is that the IMF vaguely scales with the star formation rate. So we'll come back to this, just put this in your pocket for now. Okay, so now what we'll do is we'll turn to cosmological simulations. This is to give us some idea of what the typical star formation rate history of different type galaxies are. So what I plot here is redshift, or I guess redshift. This is today in time. Halo mass, star formation rate, turnover mass, and we'll ignore this for now. This is mass to light ratio. This is a galaxy that forms, this is the evolution of a galaxy that's a little more massive than the Milky Way at redshift 0, just for reference. And this is a very massive galaxy at redshift 0, which is the one we'll focus on, the red line. So the massive galaxy at redshift 0 peaks in its star formation rate somewhere around redshift 2 or redshift 3. It's somewhere about 100 solar masses per square parsec. The average density within these very massive galaxies at this redshift is something like 10 to the 5, and this is H2 density. So this means that the gas temperature is more or less comparable to the dust temperature. And of course, the dust temperature in a very heavily star-forming galaxy is very large, which means the temperature is very large, which means the gene's mass is large. If I say the turnover mass in the IMF scales with the gene's mass, that means that the turnover mass will be very high, here about 1 solar mass. For reference, the purple line shows the Krupa 0.5 turnover mass. So you can see that at redshift 2, this massive galaxy, just for forming stars very heavily, will have a top-heavy IMF, or a bottom-light IMF, if you will. So we can see what this does with some of the aforementioned problems. If we re-examine the star formation rate stellar mass relation, here we'll look at just redshift 2, and this is for assuming a Krupa IMF. These blue points show simulated points, and these crosses show observations. And as I mentioned before, there's a distinct discrepancy between the two, where the star formation rates of observed galaxies are a factor of a few too high compared to the observations. Now, because I know that the IMF in these simulations scales with the star formation rate because of dust heating and then therefore gas heating at high densities. And I can run population synthesis modeling to figure out how the luminosity of a stellar population scales with the IMF. I can construct some relation for a top-heavy IMF, or an IMF that varies with the ISM properties, between star formation rate and the bolometric luminosity. And this comes out to be something like slightly sublinear. For those of you who can't read it, the exponent's about 0.9. And of course, for an invariant IMF, this exponent would be linear. So what this means is that for a very heavily star-forming galaxy in a local universe, say like a ULIRG, forming stars at 100 solar masses per year, this suggests that maybe the correction would drop the actual star formation rate down to something like 80. Not a big correction, but a correction. And for maybe something like a sub-millimeter galaxy forming stars at an inferred rate of 3,000, this would drop it down to 1,000. I mean, still an extreme beast, but not quite as extreme. So applying this sort of correction to the inferred star formation rates from the observed galaxies, going from a Krupa IMF then to the model IMF, we see that the observed galaxies come into much better agreement with the simulated points. We can play the same game with the cosmic star formation rate history if you believe that this discrepancy does exist. This is, again, the directly measured star formation rate history as a function of redshift. This is what one would infer from stellar mass density measurements and assuming a Krupa IMF. And this red line here is what one gets from, quote, correcting the observed star formation rate density with our model IMF. And at redshift 0, to note what a difference this makes, the difference between the purple line, the Krupa IMF, and the stellar mass density measurements in the blue line results in about a factor of 2 difference in the number of stars formed by redshift 0. When one uses our model IMF, this results in a difference of a factor of about 1.3. So it's a pretty substantial difference, though it doesn't actually fix the quote problem. The most important part, I think, of this model is what happens to the redshift 0 galaxies. Because, again, as Charlie just spent some time telling us, the redshift 0 galaxies, somewhat convincingly have a bottom-heavy IMF. So if we now look at this same massive halo, this red line, and we look at the star formation rate as it approaches present day, the star formation rate plummets, right? It's much less than a solar mass per year. And if we take a Milky Way star formation rate of something like 2 solar masses per year and assume that the cosmic ray flux scales linearly with the star formation rate, then the cosmic ray flux drops drastically as well. And when the cosmic ray flux drops in a very low density environment like an elliptical, and when I say low density, I mean the gas, then the temperature drops because the temperature in low density environments is dominated by cosmic rays. So the temperature can drop from the average 10 Kelvin that one sees in a Milky Way-like galaxy down to something like 6 Kelvin, 5 Kelvin. And this makes a difference in the critical mass. So then if I assume the turnover mass scales with the Jeans mass of the molecular clouds, again, this is a Krupa line here for redshift 0. This galaxy, which was top-heavy at redshift 2, now drops to being bottom-heavy by redshift 0. And this makes a small difference, but a noticeable difference in the mass-to-light ratio. So plotting in the same units that Charlie showed, this is the K-band mass-to-light ratio normalized by a Milky Way mass-to-light ratio. And if we look at the red line, again, by redshift 2, this has a very low mass-to-light ratio, and by redshift 0, it has a slightly higher mass-to-light ratio than a Milky Way-like galaxy. Plotting it a little more quantitatively in comparison to what Charlie just showed us, these are the same points he showed us for his mass-to-light ratio as a function of sigma. The blue and red points are his data, and then the triangles are simulated galaxies. And you can see the normalization may be arguably off, but the trend is in the right direction. As you go toward more and more massive galaxies, you tend to get more and more bottom-heavy IMFs. And the reason for this is fairly straightforward. I'm only plotting 2 halos here, but as you plot more and more massive halos, the peak star formation rate epoch shifts from closer to present day to early and earlier times. And then you go through a much longer period of the bottom-heavy IMF as the star formation rate plummets below a Milky Way value. So the basic idea then, in conclusion, I think I'm finishing just about on time, is that this is obviously I've had to make one pretty severe assumption regarding the IMF, and that's that the IMF varies with the molecular gas properties in a galaxy. If that assumption is reasonable, then what you find numerically is that at very high densities, the gas-dust coupling that occurs at high densities can drive temperatures to be very high. And this can give you very high Jeans masses, and then this can give you, under this Jeans assumption, a very top-heavy IMF, which many people argue one needs to solve a number of problems at high redshift. As these massive halos then go into their golden age and form stars at very low rates toward present epochs, the densities decrease and cosmic rays tend to dominate the temperature profiles. Low cosmic ray fluxes then drive low temperatures, which give you low IMFs, and then gives you an increasingly bottom-heavy IMF as you go toward more and more massive galaxies. Of course, this all is dependent on whether or not this statement is actually correct, that the genes properties of GMCs relate in any way to the IMF. Thank you.